The physical structure of a biological brain and the architecture of a silicon processor are completely incompatible. One is a wet, highly connected web of living tissue. The other is a rigid grid of metallic switches, processing discrete zeros and ones. For decades, scientists tried to bridge this gap using the interdisciplinary hexagon from the 1978 Sloan Report. This theoretical model defined cognitive science as a collaboration between 6 separate fields: philosophy, psychology, linguistics, AI, neuroscience, and anthropology. That model is obsolete. A linguist mapping syntax and a neurobiologist mapping synapses are studying the exact same mental process, but their isolated frameworks cannot explain how biological tissue actually produces an abstract thought. This theoretical failure is hitting a hard technological wall. Traditional von Neumann computing, where a central processor executes logic sequentially, one step at a time, cannot simulate the parallel, intertwined nature of organic cognition without choking on the computational load. To bypass this bottleneck, the hardware infrastructure is shifting towards right brain computing, or RBC, a paradigm scheduled to reach industry maturity by 2026. Instead of relying on sequential logic gates, RBC systems process information simultaneously. They use stochastics and physical resonance, leveraging the actual physics of the hardware, like light waves and optical oscillations, to solve complex math problems natively. This new hardware requires an entirely different software framework, known as Multicode 6.0. Multicode 6.0 abandons the scattered hexagon. It relies on multi-type and multi-granularity semantic learning, a method that trains systems to understand information across multiple structural levels at the exact same time. To see how this architecture functions, we need to examine this new stack layer by layer. We will begin at the top with algorithmic logic, descend into the middle layer of probabilistic inference, and finally reach the foundational layer of physical physics. To understand the future of artificial intelligence, we have to stop treating the mind as software running on passive meat. The brain is an active, self-sustaining resonant cavity, and our hardware is finally being built to mimic it. The top layer of the cognitive stack is built on the mathematical logic pioneered by Alan Turing. He established the Turing machine concept. This was a mathematical proof demonstrating that any process that can be described as an algorithm can be executed mechanically, step by step, regardless of the physical material doing the calculating. Cognitive scientist Douglas Hofstadter expanded this formal logic to explain the origins of intelligence itself. Hofstadter proposed that consciousness originates from a strange loop. A strange loop is a hierarchical system where moving up through ascending levels of abstraction suddenly and unexpectedly routes you right back to your starting point. In this model, the feeling of I is not a physical object in the brain. It emerges entirely through this recursive feedback mechanism, occurring the moment a formal system becomes complex enough to perceive and reference itself. This relies on isomorphism within physical symbol systems. Isomorphism is a strict structural mapping between two distinct systems. Meaning doesn't exist inherently within the system's symbols. It crystallizes only when those internal symbols map perfectly onto the external reality. Early artificial intelligence relied entirely on this approach. Programs like Terry Winograd's SHRDU could understand complex language and execute logic flawlessly, provided they were operating inside a rigid, highly controlled digital environment composed of simple virtual blocks. But biological organisms do not live in rigid block worlds. They operate in highly unpredictable environments, filled with sensory noise, ambiguous data, and constant physical threats. While formal symbol manipulation provides the structural syntax for thought, strict rules shatter upon contact with real-world chaos. To survive, biological systems had to evolve a distinct secondary layer of probabilistic error correction. This middle layer is defined by Andy Clark's theory of predictive processing. He describes the brain not as a passive receiver of data, but as meat that predicts. Under this model, perception is a controlled hallucination. The brain generates a constant stream of top-down predictions about what is out there, which then collide with the incoming sensory data. The difference between the two is the prediction error. The math driving this engine is Bayesian inference, calculating probabilities based on prior knowledge. This equation shows how the brain acts as a statistical estimator. It takes a prior hypothesis, factors in new sensory evidence, and computes the mathematically most likely reality. The singular biological goal within this framework is to continuously minimize those prediction errors, keeping the organism mathematically aligned with its environment. The brain resolves these errors in two ways. The first is perceptual inference, where the system simply updates its internal model to accept the new sensory data. The second is active inference. Instead of changing its mind, the organism moves its body, altering the physical environment until the incoming sensory data matches the original prediction. Because the system relies on distributed probabilities rather than strict formal logic, it features graceful degradation. If part of the network is damaged or visual input obscured, the system still functions reliably by relying on its broader statistical priors. Bayesian prediction successfully manages the uncertainty of the physical world. However, updating thousands of interconnected probabilities simultaneously creates a massive processing load. Without a central CPU to coordinate the timing, there must be an underlying physical mechanism allowing billions of distributed neurons to execute this math instantly. The foundational layer of the multicode stack bridges the gap between abstract probability and physical matter. This is the domain of general resonance theory, or GRT. GRT posits that cognition's binding mechanism is shared resonance. When physical structures vibrate near each other, they naturally couple and achieve synchronized field coherence. In a biological system, this shared resonance triggers a phase transition. Instead of sending information slowly via chemical pathways, the synchronized field allows data to flow at massive bandwidths almost instantaneously. The biological hardware executing this includes structured water acting as waveguides and DNA acting as fractal antennas, creating vast electrochemical and electromagnetic resonance cascades. This visualization maps the mathematics of that synchrony using Kuramoto-type phase reduction. This energy functional equation describes how a network of oscillators minimizes its spatial phase gradients to reach a stable state. By minimizing that energy, the resonant lattice stabilizes a global order parameter. This acts as an emergent, decentralized clock, coordinating the timing of cognitive processes across the entire brain without needing a master CPU. This physics is engineered into right brain computing's coherent Ising machines. The Ising model Hamiltonian equation shows how they solve complex problems. By utilizing nonlinear optical oscillations and resonant coupling, they settle into the lowest energy ground state, bypassing traditional logic. Under the combination hypothesis of general resonance theory, this specific physical coupling serves as the binding mechanism that fuses individual micro-units of data into a unified macro-conscious experience. Resonance is the physical medium. It executes the Bayesian math, which in turn provides the flexibility needed to generate the self-referential strange loops of formal logic. These three layers fuse to form the Multicode 6.0 architecture, mapping cognition from the logic of software down to the physics of hardware. The predictive processing layer is already driving real-world applications, most notably with the 2025 brain-computer interface developed at Stanford. By applying recurrent neural networks, AI architectures designed to recognize sequential patterns, this system successfully decodes inner speech directly from the brain's motor cortex. Operating over a 125,000-word vocabulary, the interface achieves a 74. Unlike traditional passive electrodes, these organic nanowire systems dynamically react to the fluctuating chemical and electrical environment of the human brain. This establishes a true symbiotic coupling. The artificial and biological neurons physically synchronize their signaling, directly demonstrating the axioms of general resonance theory in vivo. Multicode 6.0 has transitioned from a theoretical framework into the active engineering blueprint for integrating artificial intelligence directly into the human nervous system. The adoption of this resonant framework does face philosophical pushback, primarily centered around the zombie resonance problem. Materialist critics point out that while gamma synchrony and face locking are observable in the brain, they may merely be physical correlates. There is no empirical proof that syncing the vibrations of nanowires and neurons actually creates subjective experience, leading many to reject the panpsychist implication that all resonating matter possesses a baseline consciousness. Despite epistemological debates, the era of von Neumann computation is ending. To build the next generation of artificial general intelligence, We are shifting from machines that merely compute data to architectures that mathematically resonate with reality.